Now we're going to find out the electric field due to a line of positive charge. It is an infinite wire which is positively charged, and at a certain point, maybe at this point, which is at a distance r, you need to find out what is the electric field. And what is given is that the length of this wire is infinite and it has a charge density is constant. I hope you remember what is charge density. It is charge per unit length. So we are going to solve it by Gauss's law, and because it is a wire, so first we have to think which kind of Gaussian surface we should draw on it. So, and also because it is a positively charged wire, because you know that a positive charge has an electric field away from it. So for this wire, the electric field will be away from it. So this will how the electric field should look like from this wire, and this will be in all the three different directions, but because we are working on a paper, so we can just draw in both the sides. So at this point we have to find out what is the electric field. So the first thing we are going to draw is draw a Gaussian surface, and for this kind of geometry a sphere will not be a good Gaussian surface, so we are going to draw a cylinder. So on this wire, this Gaussian surface, it will be a cylinder. Okay, and the radius of this cylinder will be r. And at each area, like for this, the area vector, so the first thing is to draw the Gaussian surface. So we've drawn the Gaussian surface. The second thing is to check the direction of electric field and the area vector. So you know that at this point the electric field will be radially outwards, and area vector, because it is a cylinder, so the area vector will also be in the same direction, because area vector is also along the radius. I have tried to make an analogous situation to this one. It is a hairbrush. So it can act like, it seems like this is, it can be compared to a positive charge or a charged rod. And the electric field is in all the possible directions, and this paper around it, this will be a Gaussian surface around the wire, and you see that the electric field will always be along the radius. And if we have to check what is the electric field on this, it will be along the radius. So at each point it will be something like this. Okay, electric field will be always along the radius. Similarly, now this is the surface, and the area vector will always be along the surface at every point. So it means that area vector and electric field vector, they will be in the same direction. So if you just have to draw this cross section from above, if you just have to see the cross section of the wire, the electric field and the Gaussian surface, it will look like a positively charged wire. It will look something like this. Okay, so this will be the cross section of this positively charged wire. Suppose that if this is a positively charged, rod inside, okay, and this will be the Gaussian surface. So from here we understand that electric field and area vector, they will be parallel to each other. So we know the angle between electric field and area vector, and here at these surfaces area vector will be perpendicular to the electric field. Similarly, so we will not consider these areas because here the area vector will be perpendicular to the electric field. So E vector is perpendicular to dA vector here also, and even here also E vector is perpendicular to dA vector. So when we write Gauss's law, it is E vector dot dA vector. So it will be this area, and because they are perpendicular, so it will be 0 plus this area, the product will be 0 again, plus E vector dot dA vector, because they are parallel to each other, so E dA cosine of 0, it will be 1. So this will be the entire integral. Okay. Now by the same logic that this R is a constant, so the electric field at each of these points, because the charge is constant. Now suppose that charge from here to here, suppose that it is capital Q, okay, and the length of the wire is L. So the electric field will be constant at these points because R is constant and the charge inside is constant. So in this integral we can again take electric field outside and area vector. So now the total area of the surface will be this curved area. We just have to take into account this area. So it will be the circumference and the length of this area, which is the Gaussian surface. Okay, so we just have to find out this total area now. So this total area will be the circumference into the length of the cylinder. Okay. So now this is the first part of the Gauss's law, and now the charge inside the Gaussian surface. Now the charge inside the Gaussian surface is capital Q. So then the Gauss's law turns out to be E vector dot dA vector is equal to charge upon epsilon naught. It will be E into 2 pi R L. And because you know that lambda is given to be charge per unit length and it is constant, so it will also be, it should be equal to Q upon L also. So Q can be replaced by lambda L, 2 pi R L into E. L will cancel with L and electric field will be lambda upon 2 pi epsilon naught R, and just multiply with 2, divide with 2, so this term, it is KE, so it will be 2 lambda KE divided by R. So this will be the electric field due to a charged wire at a distance R, where I suppose you know what is KE, 1 upon 4 pi epsilon naught, a constant.